Have you ever wondered why a straw in a glass of water appears broken at the waterline? Or why a fish in a pond seems to be in a slightly different position than it actually is? These everyday occurrences are due to a fascinating phenomenon called refraction. Refraction is all around us, subtly shaping our perception of the world. It's the reason why eyeglasses can correct vision, cameras can capture images, and telescopes can peer deep into the cosmos. Understanding refraction unlocks a deeper appreciation for the intricate dance of light and matter. Refraction occurs when light waves pass from one medium to another, such as from air to water or from glass to air. Light, despite its ethereal nature, follows specific rules as it travels through different materials. One fundamental rule is that light travels at different speeds in different mediums. This change in speed causes the light to bend, or change direction, at the interface between the two mediums. This bending of light is what we perceive as refraction. The degree to which light bends when it passes from one medium to another is determined by a principle known as Snell's law. This law, named after Dutch scientist Willebrord Snellius, provides a mathematical relationship between the angle of incidence, the angle at which light enters a medium, and the angle of refraction, the angle at which light exits the medium. Simply put, Snell's law tells us that the greater the difference in the speed of light between two mediums, the greater the angle of refraction. This principle allows scientists and engineers to predict and control the behavior of light in various applications, from designing lenses to developing optical fibers. Section 4. Density dilemma: optical versus mass density. It's important to distinguish between optical density and mass density, as they are not interchangeable concepts. While mass density refers to the amount of matter packed into a given volume, optical density relates to a material's ability to slow down light. A material with a higher optical density will cause light to travel slower, resulting in a greater degree of refraction. Counterintuitively, a material's optical density is not always directly proportional to its mass density. For instance, while diamond has a higher mass density than water, water has a higher optical density, causing light to bend more in water. Section 5. Trapped light: the phenomenon of total internal reflection. Under certain conditions, light passing from a denser medium to a rarer medium can be completely reflected back into the denser medium, rather than refracting out. This intriguing phenomenon is known as total internal reflection. Total internal reflection occurs when the angle of incidence exceeds a specific critical angle. At this critical angle, the angle of refraction becomes 90 degrees, meaning the refracted light ray travels along the interface between the two mediums. Beyond this critical angle, all the light is reflected back into the denser medium.